Welcome to the Reef Resilience webinar, Using the Latest Science to Design Networks of MPAs. Thanks for joining us today. My name is Sherry Wagner, and I am the Reef Resilience Program Coordinator for the Nature Conservancy and your host for today's webinar. This webinar is part of the Reef Resilience mentored online course, Resilient MPA Design, that started just a month ago in April. A few housekeeping items before we begin. Today's webinar will be 1 hour. About a 45-minute presentation followed by a question and answer session. There are two ways you can ask questions. Use the question box anytime throughout the webinar to send questions, and we will keep track of these for the end of the presentation. Or you can raise your hand during the question portion of the webinar, and I will take your question during that time. You raise your hand by clicking on the small hand icon on the toolbar to the left of your name. If you're having any technical difficulties, such as trouble hearing or seeing the slides, you can send us a message via the question box and we'll try to help you resolve it. I would now like to introduce and welcome today's presenter. Dr. Allison Green is a senior marine scientist for the Nature Conservancy. Over the last few years, she has provided scientific advice and training in resilient MPA network design for field practitioners in over 20 countries in the Western Pacific, Southeast Asia, West Indian Ocean, and the Caribbean. Currently, she is focused on providing technical assistance for MPA network design in the Coral Triangle and Micronesia. Her areas of expertise include integrating fisheries biodiversity and climate change objectives into resilient MPA network design, coral reef fish ecology, coral reef assessment and monitoring, and measuring the effectiveness of marine conservation. Prior to joining TNC, Ali was the director of the Science, Technology, and Information Group at the Great Barrier Reef Marine Park Authority. She has a PhD from James Cook University in coral reef fish ecology and lives in Brisbane, Australia. Thank you everyone for joining us today, and thanks so much for speaking with us today, Ali. And right now I'm going to change over the presentation to you and let you get started.
Okay. Good morning, everybody. I'm going to do my best to get this right. Sherry's shown me how to do it, so here we go. Okay. Well, good morning, at least it is morning in Brisbane. Thanks for the opportunity to share with you today how we're using the latest science to design networks of marine protected areas for a range of objectives such as fisheries, biodiversity and climate change. Now I know that you've all gone through the online training for this module already, and so many of these concepts you will have heard before. What I'd like to do today is to go through a presentation with you so you can see how I would explain this to stakeholders, and then to give you this presentation with speaking notes so that if you want to give a similar talk, you've got something that you can use and you just need to update the photos for your area. I'm also going to give you a couple of case studies of how this information has been used recently. So why are we doing this? Well, marine protected areas can be important tools for achieving multiple objectives. They can be very useful for protecting biodiversity in the face of climate change and for natural resource management, such as for fisheries and tourism. Of all the different sorts of MPAs, Notake Areas are the most powerful tool we have. Now, Notake Areas are known by different names. I often call them marine reserves. Other places call them fish refuges. But essentially, they're areas where you can't take anything out of the area. And what I'm going to do today is actually focus my talk explicitly on these Notake Areas because they are so powerful, and hopefully show you why they're so useful and how we can design them better. So what I'm going to start now is first of all tell you about why I'm focusing on Notake Areas and why they're so powerful. The reason is that there are a lot of ecological benefits that accrue within these areas quite quickly after protection. Inside the Notake Areas, you rapidly get an increase in diversity, density, biomass, body size, and reproductive potential of many species, particularly key fishery species such as these ones here from the Caribbean. And that's great if your objectives are for protecting biodiversity or climate change adaptation or tourism, but it's not going to help you if your primary objective is fisheries management. But Recently, there's been an increasing body of evidence that shows us just how important these no-take areas are for supporting fisheries through the export of eggs, larvae, adults, not only to other reserves but also to the fished areas. I'm going to quickly show you now a couple of animations of how no-take areas work, which you might find useful at your place. This one is from the Great Barrier Reef, and I'm using a coral trout, which is the #1 food fish on the Great Barrier Reef. It's a grouper. What you can see here is 2 areas of reef. If you close one of these areas to fishing, the green zone, and leave the other area open, what you see quite quickly within a couple of years is a rapid build-up in the density, biomass and reproductive potential inside the no-take area and not much change outside. Then over time, what happens is that fish don't like to be crowded, so they spill over to the fished areas where they're available for fishermen to catch. And the fishermen know this. They often fish the boundaries of the no-take areas. And that's a really useful thing, but unfortunately the benefits only extend for maybe 1 to 2 kilometres because the fish don't move that far. But what we found recently that's very exciting is just how important these areas are to support the fishery through the spillover of larvae, because you have so many more and bigger individuals inside. One study on the Great Barrier Reef recently found that within a couple of years of closing an area no-take, there was twice the reproductive biomass inside, and even though those no-take areas were less than 30% of the reef area, they were providing nearly 60% of all of the juveniles that were supporting the fishery within 30 kilometres. So you can see just how important these areas are to support the fishery outside. For those of you that are from the Caribbean, I want to share with you an example from some of our partners from the Alliance of Canancan in Mexico, who've developed a great animation to show how this works in the Mesoamerican Reef. So what you can see here is if an area is closed to fishing and marine reserve on the right and it's still open on the left, you quickly get a build-up within the marine reserve in terms of the abundance and the diversity, and then once again they don't like to be crowded, so they start to spill over to outside where they're fished, and then you start to get this big reproduction and larval dispersal coming out of the reserve to support the fishery. Okay, so that's why no-take areas are so important and why I'm going to focus on them today. So no-take areas can be really powerful tools for achieving these sorts of objectives, but the problem is that they frequently aren't. And that's because they're either not designed in a way to take the ecology of the key species that they're trying to protect into account, or they're not effectively managed or enforced. Now, today I'm going to focus on how you can design these areas so they will work ecologically. And the reason I'm doing that is because one of the frequent mistakes I see when people design these networks around the world is the decisions are driven so heavily by social economic considerations that they're just not designed in a way that they will actually work to achieve the objectives. So we know that social, economic, cultural considerations are important, but for today we're just going to focus on what we need to do to make sure it works ecologically, because there's no point setting it up if it's not going to work ecologically. Now, to do that, I'm going to pull from a detailed review that we did recently on how to design marine reserves for fisheries management, biodiversity conservation and climate change adaptation. Now, through your online training, much of the training that you will have received has actually come from this review and a couple of others that I'll speak about. We did this a few years ago because we realised that if people wanted to design reserves for these objectives, there were so many different papers out there, it was hard for a practitioner to know what to do. And in particular, the design criteria tended to either focus on just fisheries management or biodiversity conservation and climate change. And while there's a lot of similarities in how you design no-take areas for those objectives, there's some key differences regarding particularly the size and duration of the areas. So what we want to do is to give advice to people who wanted to design areas to do all of those things at the same time. So what I'm going to do now is I'm going to run through some of the main principles that we recommend. Many of these you will have seen already on the online training, but I hope that you will get something out of hearing how I would explain it to your stakeholders. So the first principle is the need to represent examples of each type of habitat in no-take areas. Now, why do we do that? Well, different species use different habitats. For example, some use coral reefs, some use mangroves or seagrasses. So if you want to protect the full range of species for biodiversity protection, or all of your fishery species, you really need to protect examples of each sort of habitat in no-take areas. One of the most hotly contested decisions in any no-take area design process is how much of each you need. The way we decide that is we use the science from fisheries biologists who tell us that to have healthy, sustainable populations of key fishery species, you need to protect about 30% of the spawning adults. And you can use how much of an area you protect as a proxy for how many spawning adults you're protecting. For example, if you protect 20% of an area, you can assume you're protecting 20% of the spawning adults. But how much do you need where you live? Well, that depends entirely on your situation. It depends on how much fishing pressure there is and whether there's other good fisheries management in place outside your no-take areas. For example, if you're in a place where there's really heavy fishing pressure and there's not good fishing management outside, then you should aim for a higher percentage, maybe 30%, because that's the only place that you're going to have healthy populations of spawning adults to support your fisheries. Some people would argue for even more now because climate change is going to affect these ecosystems so much. On the other hand, if you're fortunate enough to live in an area where there's not much fishing pressure or there's good fisheries management outside, then you can aim for a lesser percentage, maybe 20%. The second thing we need to think about is the need to spread the risk. And that's because there's a number of large-scale disturbances such as hurricanes, coral bleachings that can come through and wipe out your ecosystem you're trying to protect. So you don't want to just protect one example of them. You want to protect at least 3 and spread them out so the chances they're all wiped out by the same disturbance is reduced. Here's an example of how we did this in a design of an MPA network in Kimby Bay and Papua New Guinea. These black areas are what we call areas of interest, where we're working with local communities to help them establish locally managed marine areas. What you can see here is on the west side of Kimby Bay, these blue areas are fringing reefs, and there's examples of those protected in each of a few of these areas of interest and now in locally managed marine areas. The other thing we need to do is to make sure no-take areas include critical areas for fisheries management. These could be fish spawning areas such as these groupers here or nursery habitats. And there's some great examples of how this has been done now in a few places. Here's just one from Palau in the Western Pacific. You can see this is the main island chain in Palau, and these orange things are their protected area network. And you can see 2 of these protected area networks are protecting channels, which are important spawning areas for these fish. The other thing we need to do is to make sure no-take areas include special and unique areas for biodiversity protection. They might be turtle nesting areas, or they might be remote atolls that have special and unique ecosystems and species. A great example of where that's been done is here in the Solomon Islands, where in 1995, the communities worked together to set up this Arnavan community-managed conservation area to protect critically endangered hawksbill turtle nesting there. And now, 20 years later, they're getting twice as many turtle nests as they had before. So it's been successful for that, but in doing that, they've also supported all of these reefs, and they've seen a massive increase in the number of fish and invertebrates in the area, so much so that in the areas all around here, the communities are setting up their own examples of no-take areas. The other thing we need to do is to make sure no-take areas include areas that are most likely to be resilient to the threat of climate change. So we know that climate change is going to have profound effects on our ecosystems, and we just need to think about which are the areas that are most likely to survive to protect. For example, here you might have coastal systems such as mangroves or turtle nesting areas, and you need to protect examples of those that have somewhere to move up as the sea levels rise. In terms of rising sea temperatures and coral bleaching, as I'm sure you've been through already in this training, is that some areas are naturally more able to cope with bleaching. They might be more able to cope with changing temperature and they don't bleach as badly, resistant areas, or they may bleach badly but recover really well and be resilient. So when you're deciding which areas, which are those representative and replicate examples of habitats to protect, try and choose these areas that have got the best chance of surviving. What I'm going to talk about today is how to use connectivity to design your marine protected area. Now, we've known for a long time that connectivity is one of the most important things for us to consider. And by connectivity, I mean how populations are connected demographically through the movement of adults, juveniles, and larvae. So we've known we've needed to do that for a long time, but we haven't been able to do it because we didn't have the information at our fingertips. So what we did is another detailed review of the larval dispersal and movement patterns of coral reef fish and what that means for designing marine reserves or no-take areas. Now, this review is global in scope. It's the best available information for all coral reef fishers, so you can use it wherever you're from. So what I want to do is explain how we do this. Before I do it, I just want to remind everyone about the life cycle of a reef fish because it has important implications. When you swim around a reef, once again I'm going to use a coral trout, but just imagine your favourite food fish. You see these adults here. When they reproduce, the larvae, eggs and larvae go up into the plankton where they float around for some period of time. Depends on the species, can be a few days, few weeks, a month or a few months. Coral trout is about 1 month. And while they're up there, they're growing and developing before they settle back onto the reef as juveniles, and then they spend the rest of their lives on the reefs. Now, the reason I've gone through this with you is because they have very, very different movement patterns when they're on the reef and when they're in the larvae, and this has implications for how we should design the network. Also, it's mostly the adults and the juveniles that are harvested by the fishery. So we use the movement patterns in different phases for different reasons in MPA design. The first thing we do is we set the size of the no-take areas according to how far the adults and the juveniles move. The point being is that we want them to stay protected within the no-take area throughout their lives so they can get big and fat. Why do we want them to do that? Well, the science tells us that size really matters when we're talking about reproductive output. Once again, the coral trout, but this applies to any species you can think of. When the coral trout is just reached its reproductive life, about 40 centimetres long, every time it spawns, it provides 350,000 larvae. That might seem a lot, but by the time that same fish is 60 centimetres long, it's providing 3 million larvae every time it spawns. So if you want your no-take area to protect adults so they can provide larvae to support the fishery outside, what do you want? You want an area that's big enough to have these big fat mamas. So how do you apply this in your home? Well, the thing to do is that we need to be particularly careful to think about what are the species that you want to protect in your area and how far do they move. And to do that, we can use the results of that review I told you that we completed recently. This figure comes from our review paper, and what you can see here is along the x-axis we have distance in kilometres, how far things move. And because those of you that work in miles, some of you might work in miles, we've also put a mile scale along the bottom. So what you can see here is that we've put each fish in a place that represents how far it moves, where the black numbers are for the home range of that species, the red number are for spawning migrations, the blue numbers ontogenetic habitat shifts where they use different habitats throughout their lives, and the green is for we know they move that far but we're not really sure why. So you can use that information to have very informed discussions with stakeholders. As you can see, most coral reef fish don't move very far. a couple of 100 metres to a few kilometres, but some move tens, hundreds or even thousands of kilometres. So this is a really powerful graphic that you can work with communities to say, what species do you care about, how far do they move, and therefore how big do your areas need to be? Or you can say, how big is the area you've got, and is it likely to protect the species that you care about? And in a minute, I'm going to give you an example, a case study of how we've actually done that. But before I do that, I just want to mention a couple more things. One is that we recommend that these no-take areas should be actually more than twice as far as we think they move, just because we can't be that precise. We need to give a little buffer. The other thing I wanted to mention is that when you put these no-take areas in a place, we have to really think about the location that we're putting them, because as you know, different species use different habitats. They settle onto the reef and most of them spend the rest of their lives there. And it seems so obvious to say, think about what species you want to protect and put the no-take area in the right place, but you'd be amazed how many people don't do that. It's been really frustrating for me when I go to a place and people have gone to a lot of trouble to set up a no-take area because they want more, say, coral trout to catch out here in the reef, and they put it on a patch of sand or further away just because they think they don't like no-take areas, so they don't want it where they fish. And of course it's not going to work. So when you're putting these in place, you need to think about not only how big, but are they in the right place? And the other aspect of connectivity that comes into this is that while most species settle into one habitat and stay there throughout their lives, some of them actually move. For example, these are some examples from this part of the world where we have mangrove red snapper or bumphead parrotfishes that live on the reefs. They spawn, the eggs go up into the plankton, and then when they settle down onto mangroves or seagrasses, which they use as juvenile habitats before they go out to the reef. Now, in terms of MPA design, we have to make sure that either our no-take areas are big enough to include all those habitat types to protect these species, or that you have a network that's close enough together to allow them to complete this life cycle. So what I'm going to do now, before I do that, I just wanted to say that I realise some of our folks here are from the Mesoamerican Reef or the Caribbean, and that I wanted to give you a graphic for your part of the world also. This is a grey snapper that has the same sort of movement pattern. Right, now what I'm going to do now is I'm going to shift to another presentation where I'm going to give you an example of how we have recently use this information to improve the design of a no-take area in this place called Ponape, right here in the middle of Micronesia. And Ponape is a place that has one big island and a number of remote atolls. So this area here is the main island of Ponape, the green area, and it's surrounded by a big barrier reef. And those blue solid areas are where their existing no-take areas are, or their existing MPAs are. And these hatched areas are all areas where they're thinking about establishing new no-take areas. In particular over here, there's an area called Palakia Pass that they were thinking about setting up a new no-take area, but they were thinking about just focusing on this little patch out here around the channel to the outer reef. So what I want to do is show you how we tailor-made our movement information for this place to help them make a better decision. So the first thing we did is we took that fish movement figure and we took all the other fish off and we just included the species, the fishery species that occur in Ponape. And then what we did is we said, okay, these are the fish that we have, this is how far they move. Let's look at the MPAs that you've already got and see which of these species they will protect. If you look, these red numbers here are the names of all the existing MPAs around the main island of Ponape, and you can see most of them are quite small, less than a mile across, and so they only protect a small subset of the species that they care about in Ponape. And that includes the proposed Palakia Pass was also quite tiny and wasn't going to protect many species. There are two other areas in the remote atolls which are much bigger, but they're effectively not enforced, so we're not sure how effective that they are. So what we did then is we looked at it in even more detail, and we said, well, let's look at each one of these in more detail and see just what we think that it's doing to protect these species. And we developed these scorecards for each of the MPAs. Here's one example here from a place I can't pronounce, Saputik, I believe, up north. And what you can see on the scorecard is down here, this is a map that shows each of the habitat types, the legends up the top. And this black line shows where the existing MPA is. And you can see that it includes type of seagrass meadow and also some reticulated fringing reef, so sheltered habitats. It's not very big, it's only half a mile across, and so it's only going to protect a couple of species. What we did on these scorecards is we refined that fish movement graph even further and said, okay, so of all the fishery species here, which are the ones that you are most important to you, that you most want your areas to protect? And they came up with this 8 or 10 species. So as you can see, this place is only protecting example for a couple of places. So then what we did is we used a similar approach to refine the design of the proposed Palakia Pass. Remember I said before that this was a proposed MPA out here on the outer barrier where there's a channel through the reef, and they were thinking about just protecting this dark blue area. And we looked at that and we said, well, if you do that, it's only going to have benefits to a couple of species that live out there in the pass and don't move very far, because it was only going to be a quarter of a mile across. So what they ended up doing was they ended up making this area much bigger, not only in size but also to include a lot more habitats. So not only did it include these outer reef habitats, but it also included sheltered reefs, seagrass meadows and mangroves, which meant that it's actually now going to protect a much wider group of species, including these ones here, the rabbit fishes that use these areas as nurseries. So by using the fish data with local communities, and these are local communities and fishermen, they made much better decision and they declared the area last year. So now the MPA network in Ponape looks like this with this great new place up there. So as you can see, it's really powerful information to use with people to improve the design, and we've done this now with people from all ranges, whether they're the heads of governments, senior fisheries management or local communities such as here in Ponape. And also we did a similar thing in Kenya. So there are lots of opportunities to use the science to work with communities to make better decisions. So let's go back to the presentation now. And let's go back to the larvae. Remember we talked about the larvae, and the larvae spend, in this case, about a month in the plankton floating around where they can and do move long distances. And unlike the adults and juveniles, they're really not that susceptible to fisheries catch. So it's okay for them to come in and out of the Notake area. But because they move further than the adults and the juveniles, they're really important to help us establish mutually replenishing networks of Notake areas. So we set the spacing of these areas according to how far the larvae moves. So we want them to be close enough so they're well connected. So how do we apply this? For many years we had to use fish larval dispersal models, which predicted based on the biology of the key species, such as how long they're in the plankton, and the physical features of the area, such as the currents, directions and so forth. They predicted how far they moved, and they predicted 30 to 50 kilometres or hundreds of kilometres. But recently some very clever people have directly measured how far they move, and at most species, actually, even though they can move long distances, most of them move less than 5 kilometres or 9 miles, and self-recruitment is common. So if you go to an area, 20 to 60% of the babies in that local area came from adults there. They did this using DNA parentage analysis, just like you do if you're not sure if that man's the father of that baby. You can do a DNA profile, and they do that with fish now. And this information comes from a wide range of species, everything from Nemo up to coral trout. So how do we use this when we're designing no-take areas? Well, because most of the larval connection is within 15 kilometres, it's good if you can space your no-take areas that far apart, so then they're really well connected through larval dispersal. So if one area is wiped out by disturbance, it can be replenished quite quickly. More importantly for fisheries management, it's really important that these no-take areas are close to the major fishing areas so that the fishery can maximise the benefit from the spillover of the larvae. It's also important to think about protecting spatially isolated areas, areas that are more than 20 kilometres or 12 miles from their nearest neighbours. Because they're that far apart, they're mostly self-replenishing, and that makes them quite vulnerable to disturbance. So they might be more vulnerable, therefore they might need more protection. Okay, so the last ecological concept I want to go through now is the need to allow time for recovery. And this is something that's not covered in a lot of detail in the online course you just did, but it's really important. When I go to a place and people have set up areas, they tend to make three common mistakes. One is they haven't put the no-take area in the right place. Two, it's not big enough. And three, it's not in place long enough to actually benefit the species they're trying to protect. So what we did was another detailed review of the intrinsic vulnerability of reef fish to fishing, and therefore how long they take to recover once they're protected in no-take areas such as fisheries closures. Now, there are many things that influence how long populations recover, but one of the most important one is their biology. For example, here you can see some species on the left here are less vulnerable to fishing pressure, and they recover faster because they grow fast and reproduce fast, and their populations turn over really quickly. That's an example, for example, many of the small parrotfishes or octopus. On the other hand, you can have species that are a lot more vulnerable to fishing and take a lot longer to recover because they tend to be bigger species from the higher trophic levels, and they take a lot longer to grow and turn over. Now, rather than going beyond this generic thing, idea that's been around for a while, we decided to look to see if there was any empirical data that we can actually use to do this. So what we've done is we've looked at where is there the best long-term data for how long it takes fish to recover in no-take areas, and most of that came from Kenya, the work of Tim McClanahan and his colleagues, or from two places in the Philippines, in Apo and Sumilian Islands, through the work of Gary Russ and his colleagues. What you can see here is real data. This is how long these populations took to recover in no-take areas. Along the bottom is how many years the no-take area was in place, and both of these monitoring programs we chose because they went for more than 40 years. What you can see here, as along the bottom, is how many years the area has been closed. On the y-axis, this is the recovery trajectory of the population, their biomass, with K being full recovery or carrying capacity. There's three graphs, and they're for different trophic groups. Let's start at the bottom. If we start looking at the planktivores, things like fusiliers that we get in the Asia-Pacific region, they grow quite quickly and their populations recover within about 5 to 10 years. Other planktivores, such as surgeonfish or unicorn fish, they take a bit longer, 15 years. If you go up to the green ones, these are your herbivores. If you look at the solid green lines, they're parrotfishes. In the Philippines, they recover really quickly within about 5 years, but in Kenya they take much longer, maybe 15 to 20 years. Surgeonfishes take longer than parrotfish because they are longer lived. If we look at the carnivores at the top here, you can see that the carnivores that feed on invertebrates, like wrasses, they take about 10 to 15 years to recover, but the large carnivores, such as groupers, snappers, jacks, they take much longer, generally 20 to 40 years to recover. So this is real empirical data. So what we're trying to do now is use this to inform the design of no-take areas in terms of how long they should be in place. In terms of duration, what does it mean? It means that if you want to protect the full range of species and the full range of fishery species in your no-take areas, they really need to be in place for long term, 20 years or more, preferably permanently, because if you take 20 years to build up these populations, if you open them, they go straight back to zero and you have to start again. Now, there are benefits for some short-term protected areas for specific fisheries management needs. For example, in some places people like to close an area for a few years because they have an important cultural event coming up and they want to stockpile the fish. So they might close an area for 5 years, and when they open it, they harvest it for a feast. That's a perfectly legitimate fisheries management method. It's not a substitute for long-term or permanent no-take areas, because it won't benefit the species that take much longer to recover. And as soon as you open that area, it very quickly goes back to zero unless it's very carefully controlled. So long-term permanent are the best. If you want to, you can have some additional short-term for specific fisheries management. Just as I wrap up, I just want to remind everyone, of course, effective management is really important. We need to minimise local threats and prohibit destructive activities, because otherwise, on the right-hand side here, you can see a system that's heavily degraded by runoff of dirt and nutrients, overfishing, destructive fishing. So you have unhealthy systems and poor ecosystem services for people. Versus on this side, where you have a low level of threat, you have healthy systems, good fisheries, good tourism, and so forth. How do we use this information for no-take design? Well, obviously, if you have a choice, it's much better to choose an area that's healthy to begin with, or to choose an area, if it is degraded, it's a threat that you can manage. For example, maybe it's overfished. Well, if you can manage the fishing and the habitat's okay, it's a good choice. But an area such as this, where you might have a big problem that you can't manage, such as the runoff of dirt, that's not a good choice. So it's best to avoid those areas. The last thing is just to remember, I've focused explicitly on no-take areas throughout this talk because they're the most powerful tool that we have. But they can't exist in a sea of destruction, so it's good to integrate them within broader planning and management regimes, such as large multiple-use MPAs. Here's an example from Indonesia, where the red areas are the no-take areas, and the green is the islands, and the others are different sorts of fisheries management area. One thought that I think is really important to take home from this is all of this science might seem a lot, but it's actually really good news for local communities and stakeholders, because now we know that these no-take areas can provide benefits for communities who protect them, because if they protect the spawning stock of focal species, they're the ones that are going to benefit by recruitment to their fishery. Before, when we used to think most of the larvae went 50 to hundreds of kilometres away, it was really hard to convince communities they should protect no-take areas because some other community a long way away would benefit. Now we know that if they protect the area, they're the ones that will directly benefit. But it is only going to work if they follow these ecological guidelines. If the design is driven by just social and economic considerations, then it won't work. It also has to make sure it suits these ecological criteria. And I also think that one of the battles we have ahead of us is that a lot of people don't like no-take areas because they think they're bad because they can't fish there. But actually these areas are great for communities, and in fact, if I was a fisherman, what I would want is a no-take area right next to my fished area. So I think we've got a communication issue ahead of us where we need to make sure we share this information so people change their mind and start seeing no-take areas as the best thing they can do. I just want to remind you that all of this information we provide is in the peer-reviewed literature in a series of review papers, and that we know that most people don't read papers, so what we've done is provided it in different formats for different audiences. We have, for example, a field practitioner guide, which is this booklet here, that just says the bottom line. What do we recommend you should do and why? We have a series of posters and speaking notes. All those graphics we've been looking at throughout this talk come from here. So you can have this discussion with communities about what matters to them and why, without, with just posters, without doing a PowerPoint presentation. And we also have a policy brief that you can use to share these examples with senior government officials. Now, I just wanted to mention that there's a lot of great work going on to adapt this information around the world. And right now, for example, I see that Selene is on here and Mariana was on recently. People are working to adapt these more specifically to provide the same sort of communication products for different parts of the world, such as the Mesoamerican Reef and the Gulf of California. But for now, if you want to access all these papers or documents, they're all online here at the Conservation Gateway. We're going to share this presentation with you that has the speaking notes so you can see what I would say. I think this is also going to be recorded if you need to check how I'd explain something. But if you want any of these documents, just go to the presentation and click on that image and it will take you to them. So that's it. I hope that you found that interesting and it's a useful thing for you and that you'll be able to use this information in future.